Hello everyone, welcome back to another video of Marin Maths, and today I'm going to go back to making common exam reviews, and this is common exam number 1 for differential equations, regular or honors, whatever you want. I'm just going to do like one honors problem, just to take a look at it, because it might be a little bit difficult, more difficult than the regular differential equations problems. But I'm sure you will all be fine if you're an honors student. Okay, so but if you are in regular differential equations, please watch carefully. Okay, so well, the exam is it's not entirely trivial, but it's doable. It's doable. So there are 6 questions, which is surprising because in previous exams for other courses like Calculus 2 or 1, there are way more questions. It's might be trivial to do, but it's a little bit more work. But this is actually not too bad. All right, so let's take a look. By the way, this is the September 2017 version. Okay, so there is no answer key of this exam on the internet. So if you have any questions on the ways in which I am solving these problems, just put them down on the comment section, okay? And I'll gladly answer them. There were occasions when I made mistakes on the common exam reviews, which is, I'm a human, I'm not perfect, I'm telling you. But, I'm going to try to do my best to not make mistakes this time. I tried, I double-checked this. My friend Mike double-checked this. I think it should be good. Okay, so just getting that confirmation. All right, for question 1, we got a simple, problem. Okay, so it just asks, what is the order of each of the following ODEs? Remember, ODE stands for ordinary differential equation. Indicate whether each is linear or nonlinear. So for part A, okay, we got something like this. We got y quadruple prime of x equals to y of x times y prime of x. Okay, so basically we have to classify whether this is a linear or nonlinear ODE and what is the order. Okay, so over here, some people get confused with the x's, but it just means it's a function. Okay, so you could rewrite it like, I don't know, y quadruple prime like this, right, equals to y prime. And as you can see, the highest order is the 4th order, right? It's the 4th derivative with respect to x of y. So it's a 4th order differential equation. There's no science behind it. And of course over here, because we have a nonlinear factor being multiplied by the first derivative, okay, then it's not in standard form. So it's a nonlinear 4th order differential equation. Do you agree, Mike? Okay, good. So now for part B, so let's just write, 4th order, 4th order, and then nonlinear. Because linear differential equations are usually in the standard form, which will be something like this: some function a of x, right? Or if you use t, well, you do a of t, but it doesn't matter. A of x multiplied by let's say it's a 2nd order, so the y double prime plus a sub 1 of x times y prime plus a sub 2 of x times y plus a sub 3 of x equals to, I don't know, 0 if it's homogeneous. This is standard form linear differential equation. Okay, it's 2nd order in this case. You see there is no derivatives being multiplied by some function y. So it's in standard form. Now let's look at part B. It's going to be a little bit longer, but it's actually trivial to classify. So this is basically, actually, if you have the copy, if you have access to the exam online, just look at it. I'm going to make it simpler. I'm not going to do like Leibniz notation. It's kind of long. So I'm just going to do Euler's notation. I'm going to do x cubed y triple prime plus x squared, and then y double prime plus x y prime, and then all of this plus y equals to e to the x. And of course, like I said, it's in standard form. This is one of the standard form, linear differential equations. It's a 3rd order differential equation, so you can, write that down. So that's question 1. It's actually not too hard, not too bad. All right. So for question 2, we have the differential equation y prime is equal to y minus y cubed, okay? And for part A, we have to identify all equilibria of the system, okay? So basically, where you have this derivative equals to 0. So when the differential equation y prime equals 0, we're going to be able to find some equilibrium asymptotes. So let's take a look. So what we do, we set this equal to 0, right? This is actually in terms of t, so it's y prime in terms of t. So we can set this equal to 0. So y, we factor out a y, and then we have negative out, and then we have y squared minus 1. We set this equal to 0, right? That's the first derivative. That's equal to 0, which means that we're going to find where the tangent line of whatever function y is 0. So we find that the derivative is 0 at points y equals 0, okay? 1, if we solve this, right, for 0, we set this equal to 0, we get 1 and negative 1. Okay, so those are the equilibria of the system, that's plural. Okay, so, and now for part B, so this is the answer for part A. Now for part B, we're going to draw the direction field, which is also known as the slope field. So it's just different terminology, but it's the same thing for the problem. And they give us the interval in which we're going to draw the direction field. So it's going to be from -2 to 2 and t greater than 0. We're going to draw some curves. So let's see. We have something like this, right? So we got y, and this is t. Okay. So we're going to draw 3 asymptotes because this is where we find that each of these derivatives equals to 0. So over here we had one of them. Okay, so this is one of them. We got 1 over here and -1 over here. So we got 3 equilibria. Okay. So now we're going to take into account the interval in which we're looking this. We're finding the solution. So we're just going to go from 2 to -2, right? And then for t is greater than 0. So we actually don't care about what's behind. So just worry about what's after 0. So what comes after this. Now, one good way to do this is just by plotting some values over here, or you could even plot dy over dt, okay, as your y-axis, and then your x-axis is going to be y, so that you could see the behavior of the derivative of this differential equation. And of course, it's a polynomial function, right, which has 3 zeros. So one is at -1 over here, at 1, and at 0. So if you think about it, this over here goes to 0. So let's see what happens when it's between 0 and 1. If it's 1/2, right, what's going to happen? It's going to be negative over here, and this is going to be positive, but overall it's going to be negative. So it's positive. Negative times negative is positive. Okay, and then after 1, it should be negative, right, because this whole expression becomes positive when y is greater than 1. And then this will just take over because you have a negative sign out there. So it will be something like this, right? And then over here, we know this is a cubic, okay, a cubic polynomial. So we can already predict that it's going to be like that, okay? So this is going to be the behavior, right? The end behavior. So we can base our curves over here, our y integral curves, based on this plot of our differential equation dy dt over y. So if we start from -2, right, because we have to take into account this behavior over here. So what happens when the derivative is less than -1? So from -2 to -1, it's going to be positive, but it's decreasing, right? So it's going to be something like this. So at first we have a very high slope, very high positive slope. So it should be something like this, right? And then it's going to start decreasing until it gets to -1. So it's going to be something like this. Okay? So if we keep doing that for each value of y, you're going to find out, okay, that your curve will turn out to be something like this. Okay? So that's one curve. You could draw as many curves as you need. Okay? So something like that. Okay? That's one of the, a few solutions, if you wish. Now, from -1 to 0, okay, so basically from here, oh, my apologies, this is -1, so this should be below, so right here. So it should go like that. Okay, so this is from -2 to -1. Now from -1 to 0, this is 0 over here, we're going to have a different behavior. The derivative will be negative, the slope is negative, right? Or the gradient, you know, whichever term you want, is going to be negative. So we start at a very small negative slope, right? So it's actually going to be something like this, negative, very small negative, and then it's going to start increasing. There's going to be a maximum, and then when it gets to 0, it's going to go back to 0, okay? So it's going to be at a maximum over here, and then it's going to start going back to 0, okay? So it's going to look something like, okay, something like this. So it will be like this. Okay, so that's one curve. You can draw more curves if you want. And now from 0 to 1, it's going to be positive. Then you have a maximum slope, and then you go back to 0, okay? So you start with a minimum, right? Minimum, small. You go up to a max, and then you go back to 0. So it should look something like this. Okay, so those are your integral curves. And now from 1 to 2, well, it's just going to be negative. So starting from a small negative into a large negative. So it should be like this. Okay, and now if they were to ask you, okay, you know, what type of solution would this be over here? Well, this over here is a steady state solution, okay? So it's actually asymptotically stable over here because we have converging integral curves, okay, from either side, right, into y equals 1, right? So at y equals 1, we have a steady state solution. At y equals 0, we have an unstable asymptotic okay, solution. So this actually diverges from 0. And over here at -1, we have another, okay, stable equilibria. And over here, of course, there's no, because this is not a, you know, it's not an asymptote. The only asymptotes are -1, 0, and 1. Okay, so that's it for part B. Okay, so now for part C, we're going to describe the behavior of the solutions as t goes to infinity. In particular, describe how the behavior depends on the initial conditions. Okay, well, I mean, for part C, what could you write? Well, we already know what the behavior is going to be, right? So as t goes to infinity, okay, from, let's say, 0 to 2, right? As t goes to infinity, y will approach the asymptote, you know, y equals 1. So you can write, okay, as t goes to infinity, y goes to 1, right? And then you can say, you know, for the interval, so this is going to be on the interval, you know, from 0 to 2, okay? Because that's the interval that they are, okay, we're including. And you could do close bracket over here, okay? So, and then as t goes to infinity, okay, from -2 to 0, we see that it approaches -1, okay? So y goes to -1 on the interval from -2 to 0. And of course, 2 can be included since that's how it's stated on the problem. All right, so that's problem 2. I hope you found it, you know, a little bit intuitive, because, you know, it's not that bad. Honestly, you just have to have some sort of, you know, intuition on how derivatives work. What, you know, they represent. They're just slopes, right? So you just gotta draw some slope fields. Now, problem 3 asks, solve the differential equation, okay, y prime minus 2 over t times y equals to t squared e to the t. And now the initial condition, right, this is an initial value problem, is going to be y of 1 equals 3, okay? So this is just, you know, an initial value problem. And, you know, how can we describe this? Well, this looks like, you know, a linear differential equation, first order, right? However, it's not a separable differential equation, okay? There's actually a different name for this type of differential equation, because you have, okay, a term over here that you actually have to take into account, and then you have to use integrating factors. You know, the integrating factors method is actually very useful to solve this sorts of differential equations. Mike, do you remember what this type of differential equation is called? We only know that it's first order and it's linear. So is there a, you know, there's a special name for it. I just don't remember. Okay, forget it. I'm gonna cut this part.
Yeah, wait, what the fuck is, I mean, is there any name for that other than first order linear?
Yeah, there's like a, god damn, let me see. I forgot. There's like a specific name, a special name for it. I don't remember. I mean, I don't think it's important. All right. It's trivial. It's trivial, guys. Okay. All right. So here we go. Integrating factors works like this. Basically, you multiply, okay, this differential equation on each term by some function mu of t, okay? And this function mu of t will facilitate, it will make it easy for us to integrate this, okay? So basically, we're taking advantage of the product rule, which is, we're going to do it backwards, kind of, okay? And the fundamental theorem of calculus, okay? So let's multiply all of this by some function mu of t, okay? And then over here, what the trick is that, okay, so just watch carefully. So I'm just going to distribute this. And by the way, this is already in standard form, okay? So you don't have to do anything, because the y prime over here, okay, the highest order derivative does not have anything in front of it. It's in standard form, okay? So this will be minus 2 over ty mu of t equals to t squared e to the t mu of t. Okay, so the trick here is that you have to consider, okay, what is going to be the derivative, okay, the derivative of mu of t and y. So the product of mu of t and y all together. So you have to consider the derivative using the product rule over here with respect to t. So we're going to get something like mu prime of t times y plus mu of t times y prime. So we have to compare this over here, this result. We compare it to the one, okay, result we have in here. So we got this over here. We compare these two, and we see that we have a y prime times mu of t, right? We got that. But over here we have mu prime of t times y, and over here we have, y times mu of t, okay? Oh, this is supposed to be prime, yeah, because we're taking the, no, never mind. This is just the integrating factor, right? Because when we take the derivative, we get this. But okay, over here we got this, but over here we got negative 2 over t times y times mu of t. And here it's kind of different, right? So here we actually have mu prime of t times y. So what we're going to do is basically set this expression over here equal to this expression. And then we're going to solve, okay, for mu of t, which is, it's actually a different differential equation. It's a separable differential equation. So look at this. Mu prime of t, okay, is nothing but, d mu of t, right, over dt, okay, which in this case will be equal to this mu of t times negative 2 over t. The y's cancel out, if you notice, right, because when we set it equal to each other, both of them have y's, so they cancel out. So we're going to get negative 2 over t times mu of t. We separate the variables, right? We got t's on this side, mu's on this side. So basically, you're going to get something like this. You're going to get d mu over mu equals to negative 2 dt over t. Okay? Now what's the next step? We all know. We just integrate both sides. Okay? This is an indefinite integral. So we got ln absolute value of mu of t, right, equals to, this is going to be minus t, minus 2 times the natural logarithm of the absolute value of t plus some constant c. Okay, but now for the integrating factors, the constant of, c does not really, play an important role. So usually we just let it be equal to 0, okay, because you're going to see why. So we just solve this for mu of t, and we get mu of t is equal to, if we exponentiate both sides, or if we e both sides, that's also a way to say it. We e both sides, we're going to get e to the negative 2 times, e to the ln of t, which is nothing but t. So this over here will be t times e to the c, right? Do you agree? This cancels out over here. Okay, so we got our integrating factor over here. So this should be, let me see something. Okay, so this should be, we actually, because I'm trying to multiply this together, so I can't do this. Yeah, no, this is wrong. My apologies. It's actually, look, when you e both sides, okay, when you e both sides, so it's basically e to the power of -2, right? ln of t plus c. Now, what we do here is we bring the -2 into the natural logarithm, you know, using logarithmic properties. So we get mu of t is equal to e to the ln of t to the -2, right? Plus c. And now you can rewrite this as mu of t equals to e to the c times e to the, okay, ln of t to the -2. This cancels out. So you get nothing but e to the c times t to the -2. Okay, and e to the c, we just say that e to the c is just 1, okay? So we get that the integrating factor, mu of t, is going to be 1 over t squared. This is your integrating factor, okay? So this is just part of the problem. We're not done. Now, we're going to multiply everything by the integrating factor. So we start over here. So we got d over dt of the integrating factor, which is, you know, 1 over t squared times y. So we get something like this, which equals to the derivative of the integrating factor over here. But no, actually, let's look at what we're looking at. This, yeah. So we're going to have t squared times e to the t, and then multiply by the integrating factor, which is 1 over t squared. And look at that, this cancels out. Okay, now we used the fundamental theorem of calculus, so we integrate both sides with respect to dt. Okay, and over here, this cancels out, right? The derivative is inverse to the integral, so we get y of t, okay, equals to the integral of et to dt is just et plus c, and then we multiply t squared on both sides, so we get something like this, t squared et plus t squared c. Okay, so this is the general solution to the differential equation, but you know, we have an initial value problem, so we are told that y of 1 is 3, so you know, just do the math over here, just set y of t equals to 3 and t equals to 1. So we got 3 equals to e, right, plus c. Okay, so that means that c is nothing but 3 minus e. So our final solution should look something like this. Okay, so y of t is t squared et plus 3 minus e t squared. You can factor out the 3 squared if you want. You know, you don't have to. It just looks fancier, but whatever. Okay, now for... All right, so for problem 4, we got 2 parts, A and B. We're going to solve the differential equation, okay? Y double prime plus y prime minus 6y. All of this equals to 0, okay? Now for part A, we just solved it, okay? And then we have these conditions. We got y of 0 equals to 3. And of course, we have that the limit of the function y of t as t goes to infinity approaches 0. Okay, so 2 important conditions, which is reasonable because we're going to have 2 different solutions to this problem, right? If you can spot it already. So, and then for part B, so that's part A, right? We're just going to solve the differential equation. And then for part B, we're going to find the values of y prime of 0. So what's prime of 0 in that case? And they say in that case specifically because, of course, you know, they're hinting at the fact that this has 2 solutions. Okay. Now, this is a second-order linear differential equation, and we can use, you know, a special method to get rid of this and find y. So usually what we do is because we have this very nice linear differential equation of second order is we think about like, okay, what if y is in the form of e to the power of r of t, r times t, right? So if the solution to this equation is in this form, right? And then we know that this has some constant r in front of the t, then we can just take several derivatives, right? Several derivatives, as many as we need, and then find r, okay? Because we're going to get a quadratic. So we're going to find r, and then we're going to use that, okay, to justify that this is a solution, indeed. So over here, if we take the derivative, the first derivative, y prime, okay, we use the chain rule. So we take the derivative of the inside, which is r, right? So it's just r times e to the rt, and the second derivative, y double prime, is r squared e to the rt, okay? Very convenient. Now what we do is we use this information, and then we apply it to that differential equation. So we're going to get something like this, e to the rt. I'm going to factor it because we have a common factor of e to the rt, multiplied by, okay, r squared plus r minus 6. All of this equals to 0. This is our quadratic, okay, equation that's going to determine what the values of r are. So we can factor this pretty easily, right? 3 times negative 2 is negative 6, and 3 minus 2 is 1. So that works out. So we got r, okay, equals to negative 3, and r equals to 2. Okay, so those are our two values of r, which means that we have two solutions to this differential equation. So y of t will be equal to e to the negative 3t, and y of t is also equal to e to the 2t, okay? But now we have to make sure that these solutions, okay, agree with these conditions. With the initial problem, oh, and of course, there's a constant c over here, right? A constant of integration, don't forget the constant of integration. So we have the initial value problem, y of 0 equals to 3, and the limit of this function as it goes to infinity, as t goes to infinity, approaches 0. So, immediately you can, unchart the solution, because over here the exponent is positive. So as t goes to infinity, no matter what c is, it's just going to go to infinity. So this is not one of the solutions. And you could just immediately say, okay, this is the solution. But of course you're gonna find c. So when t is 0, y is 3. So we got something like this. Okay, c equals 3. So y of t equals to 3 e to the negative 3 times t. This is the solution because the limit of this as t goes to infinity goes to 0. We got a negative exponent. So this is the solution. And of course for part b, we're just going to find the values of y prime of 0. So we just set y prime over here. Y prime, we set it equal to 0 for this specific case. Okay? That happens when r equals to negative 3, right? So let's see. We got a negative 3, okay? So, but usually it's just convenient to go from here. So just go from your answer and then take the derivative. So just take the derivative over here. So y prime, okay, of t, it's going to be negative 3 times 3 is 9, e to the negative 3t. And then we want to find when, what the values of y prime are when t is 0. So y prime of 0 is nothing but negative 9, right? Okay, so that's going to be it for them. That's part B. And now let's go to question 5. All right. So for question 5, okay, we're going to consider the differential equation dy over dt equals to 6 minus 4y plus 3t. We got an initial condition, y of 0 equals 3. And we're going to use Euler's method to approximate a solution to this differential equation with a step size of h equals 1/3. And we're going to do that up to t equals 1. Okay, so we can make a nice chart over here. We can start with values of t over here and then values of y. Okay. Well, actually t, let's do t and then let's do y prime because we're going to need y prime, so the derivative. And then we're going to do y. Okay, so let's see, we make a table of values. Okay, so we have a step size of 1/3 and we're starting from 0, right? So that means we just add 1/3 every time. So we go 2/3 and then 1. Okay, so 0, 1/3, 2/3, 1. And of course, we're going to use Euler's method. And the formula, for Euler's method is y sub n, okay, y sub n plus 1 equals to y sub n, okay, and then plus the step size h multiplied by the function, which is the derivative, right? Is the differential equation, the first derivative of, okay, t of n, okay, comma y of n. Okay, so, and of course we're going to have values of n equals to 0, 1, 2, etc. So you can have those values. Okay, over here when n equals 0, okay, we're going to find y1, right? So y1 is going to be y0 plus the step size times the derivative function times t0, okay, t0 and then y0, okay. So that's going to be what's going to happen is we're going to approximate, okay, some some line. So if it's some curve, right? I think this is going to look like an exponential curve. If I'm not wrong, it's going to be something like this, and then you're going to have some values like this is 1/3, 2/3, and 1. And so what's going to happen is you're going to draw some tangents over here, and then if the step size is 1/3, then you're going to approximate that curve using just tangent lines, right? With a step size of 1/3. If the step size is very small, as h goes to 0, well, you're going to have a pretty close approximation, okay? But yeah, we're just doing the simple way. So let's see what we get, okay? Now for y1, so in this case, here will be, when t equals 0, we know that y is 3, right? And so, no, this is the derivative. Y is 3, yeah. And then y prime, when t equals 0, well, we'll have to find what's the derivative over here when t equals 0 and y is 3. So let's see. That's going to be 0 over here, and then 3 times negative 4 is negative 12, plus 6 is negative 6. Okay? So that means that, okay, y1 is going to be nothing but y0, okay, which is going to be 3, plus 1/3, which is the step size, and then we're going to multiply that by the derivative evaluated at t0 and y0. And we found that's negative 6. Okay? So now we're going to need this in order to solve the next one. Okay? So we're going to have 3, and then negative 6 over 3 is going to be negative 2, so it's 1. So y1 is going to be 1. Okay? So this is going to be, let me just label this. This is y0, right? y1, y2, y3. Okay. Now what's the derivative evaluated when t equals 1/3 and y equals 1? Well, over here, when t equals 1/3, 3 over 3 is 1. Okay? And then when y equals 1, well, we got negative 4 plus 6, that's 2. And then we have 2 plus 1, right, which is 3. So that's going to be the value of the tangent, the slope. So we got that y2 should be equal to y1 plus the step size times the derivative function evaluated at t1 and y1. Okay? So we know that y2 then is equal to y1, which is 1, plus the step size, which is 1/3, and then the derivative at this point, which is 3. And look at that, we get that y2 is 2. Okay, now the derivative evaluated at t equals 2/3 and y equals 2 is going to be, okay, let's see, 2/3 over here, we get 2, right? And then when y equals 2, we get negative 8 plus 6 is negative 2. Negative 2 plus 2 is 0. Okay, interesting. The value of the slope is 0 at that point. So if you think about it, this is 1/3 and it's 2/3. So it kind of makes sense that it's going to be 0, because this is kind of like the shape of the graph. Okay, if you plot it on Desmos, so you can solve the differential equation using the integrating factor method and put it on Desmos, and you will see it's going to be something like that. Okay. Now, we're going to find y3, our final value for y, and then we're going to have that this is going to be equal to y2 plus the step size, and then multiply by the derivative at t2, and then y2. So y3 is going to be y2, which is 2, plus 1/3 multiplied by the derivative, which is 0. So it's going to be 2. Okay? And the derivative at this point, well, let's see. It's going to be at t equals 1 and y equals 2. So that's going to be 3, okay? And then negative 4 times 2, well, that's going to be 0 too. Look. Yeah. No, actually, let's see. Because it's going to be 1, so 3, and then negative 8. So that's going to be negative 2. Negative 2 plus 3 is 1. So it's going to be 1. Okay. So this should be the solution to this, differential equation using Euler's method. Okay, I think my professor went over this problem that I'm going to do, problem 6, earlier today. So it shouldn't be too bad. Okay, so for problem 6, we have the radiocarbon dating used in archaeology and anthropology is based on the radioactive decay of carbon-14, which appears in trace amounts in all living tissue. If Q of t is the amount of carbon-14 in a sample, then Q of t evolves according to the differential equation, dq over dt equals to negative r times q. Negative r is some rate constant, okay? And then q is the quantity, okay? So now, for part A, okay, we're going to have to suppose that you're trying to date a scrap of papyrus found in a sample buried in an ancient Egyptian pyramid. State the dimensions and some appropriate units for the quantities Q, R, and T. Okay, so, all right. I mean, the dimensions, so that's something a mistake I made before was that I just put the units, right? I mean, the dimensions are basically asking like, okay, what type of unit it is, right? Is it time? Is it a quantity of mass? Okay, so over here, the units of Q, okay, should be, the dimensions of Q should be mass, right? Because this is the trace amounts. These are the trace amounts of whatever, papyrus we're trying to find the data of. And now this is going to be in grams. Let's just say in grams, right? Because there are small amounts. Now the units for T, of course, should be in time. And let's say now over here, if you look at part C, the units that they are, talking about are in years. So, let's just say years. Okay. And of course, for the rate constant R should be 1 over the time. So it's the inverse time, and then they should be 1 over years. Okay, that's part A. Part A is easy. Now for part B, asks if the quantity of carbon-14 at t equals 0 is Q0, what is Q of t? Well, that's very trivial actually, because they're giving you an initial value problem. So basically Q of 0 equals, Q0. And then you just solve the differential equation, just separation of variables. So you have dq over q equals negative r dt. You integrate both sides, okay? And you get natural logarithm of q, okay, absolute value, equals to negative rt plus c, okay? So you got q of t equals to e to the negative rt multiplied by e to the c. Now when t equals 0, q of t is q0. So q0, okay, is equal to e to the c. So in other words, our function of quantity at a given time t should be equal to e to the negative rt multiplied by q0. Okay, so this is basically our function q of t. I think that's the question. Okay, so yeah. Now for part C, the half-life is the time t half for the amount of a radioactive material to decay by 1/2. For example, such that Q of 1/2 equals Q0 over 2. So basically Q of T 1/2 equals Q0 over 2. So it's basically half as much material that you have in the beginning. So now we have that if t half, okay, so t half equals to 5,730 years, then what is r? Okay, so what is r? And then be sure to include units in your answer that match with part A. And yeah, let's see. So over here we know that this is going to be our value for q of t when t equals t halves. So we just go back to this equation over here and we get something like this. So we get q0 over 2 equals to e to the negative r t halves, and then of course multiplied by q0. Now the q0's cancel and we get something like, okay, natural log of 1/2. We take the log of both sides, right? Equals to negative r t halves. Okay, and we're looking for r, right? So r should be equal to natural log of 1/2 divided by t halves. Now the negative can go inside of the log as a power. So this is nothing but natural log of 2 divided by t halves. And of course t halves is 5,730 years. So it's natural log of 2 over 5,730. And the units should be 1 over years for r, okay? So that's part C. It's not too bad. All right. Now, all right, so that was the practice exam. That's it. You know, that's the 2017 version. And now, this is, you know, just an aside. I'm going to do what is my favorite problem, you know, in the entire semester. Well, not really. You know, the time since we started differential equations. This problem is problem 21 on, I think it's homework problems from section 2.4, I think. Yeah. So the problem goes like this. This is, you know, one of the tougher problems where you actually have to apply, you know, concepts from another subject, concepts from physics, actually. So you gotta use mechanics. And it goes like this. So a body falling in a relatively dense fluid, you know, oil for example, is acted on by 3 forces. A resistive force R, okay, so we got resistive force R, okay. A buoyant force of V, and its weight W, okay. So this is due to gravity, right? W is due to gravity, so this should be, you know, mg, okay, if the mass of the object is m, right? Now, the buoyant force is equal to the weight of the fluid displaced by the object. So essentially, okay, we're going to say that B, okay, is equal to, you know, weight of fluid displaced. And later on, we're going to take a look, you know, at what that means a little bit more deeply. And over here, for a slowly moving spherical body of radius A, okay, so we got basically a ball with radius A. The resistive force is given by Stokes Law. Okay, so basically R should be equal to 6 pi times some constant mu times the radius A times the absolute value of the velocity, okay, where V, okay, velocity, and mu is the coefficient of viscosity of the surrounding fluid. So in which case, if we are submerging this, we're putting this ball, we're throwing it into oil, then the viscosity of oil should be described by mu. And yeah, now for part A, so this is a pretty interesting problem. Okay, so for part A, we're going to find the limiting velocity. In other words, the terminal velocity of this sphere, okay, with density rho. So the density of this sphere is rho, okay, and it's going to be freely falling, okay, on whatever medium which has a density of Rho Prime. So basically, let's make a little drawing over here, and then there's this fluid in which it is submerged, right? Now the density of whatever fluid it is, right, if it's oil, it's Rho Prime, okay? So that's going to be the density of that fluid. And okay, so we're going to find the terminal velocity. So we're going to find vt, or limiting velocity. So it looks like we're going to have to use a limit, of the velocity function as it goes to infinity, as t goes to infinity, and then we'll be fine. Now, we have three forces. We got the force of gravity going down. So this is the weight, in other words, mg. Okay? And also, we got the buoyant force, which actually goes opposite, goes outwards. So this is B, the buoyant force. Okay? And we know that's going to be the weight of the fluid displaced. Okay, so let's wait a little bit. I'll tell you what that means. Now we also have the resistive force, okay, which is R. And of course the resistive force means that, it's resisting motion. So it's going against the motion of the object, in this case the ball. So it should go in the same direction as the buoyant force. Okay, so this is the resistive force R. And we know it's described like this equation, Stokes Law. Okay, now let's think about what the densities of each of these objects is. So the density of our ball can be described by rho. And remember that density is mass over volume. So in this case, if the mass of the ball we say is m, so the density should be m divided by the volume of the sphere. And the sphere has a radius of a. And of course, if you want to be fancy, okay, I can integrate I can prove to you that with integrals what the volume of the sphere is. So let's say, that we have some semicircle, right? So we're going to make a little coordinate axis over here, and we go from negative a to a, right? So this is the radius, and so we're going to have a semicircle, and we're going to revolve this circle about the x-axis. So we're going to find the volume of the solid generated when we revolve, okay, this function, which actually should be described by, okay, y is equal to the square root of, okay, a squared, right, minus 8x squared, okay? This is going to be, the function that describes the volume of a sphere. Now, we're going to revolve this about the x-axis in order to get the volume, okay, of our sphere. So let's go ahead and do an integral. So we can say that this over here is going to be our radius function, okay, r of x, and we're going to find what pi times r of x squared times dx, which is going to be the thickness of the disk, okay, of the volume of rotation, and we're going to add it up from negative a to a. So integral from negative a to a of pi of r of x squared dx, and of course r of x squared in this case should be y equals to the square root of a squared minus x squared. So we have something like this. We got that the volume, okay, of the sphere is going to be integral from negative a to a. We can bring the pi out of a squared minus x squared dx. Okay? Now, this is really easy to do because, it's just all you have to do over here is, just integrate this. This is pi times, okay, a squared times x, right, minus x cubed over 3 from negative a to a. And of course, because it's an even function, you can take advantage of that, and you can say that's nothing but the integral from 0 to a and then multiply by 2. So just put a 2 in front and make this 0. Okay, now just solve for the limits. So this is 2 pi and then times a squared times a, which is a cubed, minus a cubed over 3, and then all of that minus 0. So you find the common denominator. That's going to be 2/3. 2 times 2 is 4. So yeah, 4 pi a cubed over 3 is the volume of a sphere. Proven, right? Do you agree with me? Okay. Well, let's see. Now that we know the volume of a sphere, we can put this down here. So we can say that this is nothing but the mass divided by 4 pi a cubed over 3. Okay. So, where is my eraser? Okay, here it is. Now, what is Rho Prime? Well, Rho Prime is the density of the fluid, right? And we could just assign some dummy variable, right, for the mass. can say this is just m, medium, m of m for medium, right? Divided by the volume, which in fact is the same volume as the sphere, right? We can say it's the same volume because we're just we only know, okay. This is going to be 4/3 pi a cubed. It doesn't really matter what the volume is. We could say whatever it is. There's really no, no difference. Okay. Now, but I think this should be, because it's in a bucket. It's in a bucket of whatever liquid it is. I think the volume shouldn't be equal to that. So let's just call it V for medium. It doesn't really matter. Okay, so that's rho prime. We have rho, and we're trying to find what's the terminal velocity, right, of this freely falling object. So let me just erase this. Okay, so what do you think we should do? Well, first of all, we need to describe our buoyant force. The buoyant force is the weight of the fluid displaced. And of course, the fluid that is displaced over here, is equal to, in volume, as the volume of, the ball. So that's why I was saying that the volume could be equal, but it doesn't really matter. So for our purposes, the volume will be equal to that. So that's going to be rho prime, so of the fluid displaced. Okay, so basically, we can say that the mass of the medium, is going to be equal to rho prime, times 4/3 pi a cubed. Okay, and now over here, the weight of the fluid displaced, well, that's nothing more than the force of gravity. So that's going to be mg in this case. The buoyant force then should be equal to rho prime 4/3 pi a cubed times the force of gravity. Okay? So that is going to be our buoyant force, which is going to go upwards, right? So we got all three forces sorted out, okay? So we got W equals mg, we got rho equals, the resistive force R equals 6 pi mu a times the absolute value of V, and we got the buoyant force. Now, we can apply Newton's second law, which says that, the sum of the forces, is going to be equal to the mass of the system times the acceleration, And of course, over here we're only looking at the mass of the ball, so the system is the ball, so let's just call it m. Now, that's going to be equal to, if we choose the direction of motion to be positive in the down direction, then we can say the following. We can say that the sum of the forces will be W, W minus R minus B. And that's because we're choosing the down direction to be positive. Okay? Now remember that, because we have different forces, we have a force that is actually proportional to velocity. Well, the velocity is not going to be constant. So we can write this as a differential equation. And we can say that this is nothing but m dv dt equals to the weight minus the resistive force minus the buoyant force. Now we can rewrite all of this using all expressions. So m dv dt, equals to the weight, which is going to be the mass of the ball times g, minus the resistive force 6 pi mu a times the absolute value of v, and then minus the buoyant force, which is rho prime, 4/3 pi a cubed times g. Now over here, I feel like we can rewrite this m value over here in terms of the density rho of the ball, But we can do that later, so don't worry too much. This is just to show you what the equation should look like. Now we divide everything by m to find, the standard form of this differential equation. So, so we're going to have something like this. We're going to have dv over dt, and then we're going to add the term that has the velocity on it on the other side in order to have a standard form. So we're going to have plus 6 pi mu, and then times the radius a, times the velocity v, and then we have divided by m, right, the mass of the object. All of that's going to be equal to g minus rho prime times 4/3 pi a cubed multiplied by the force of gravity. I mean by the acceleration of gravity. Now, this is a standard form differential equation, and we can use the method of integrating factors, right? Because look at this. We got the v prime plus some constant times v, okay, equals to some constant. Okay, so immediately from this, we can see that the integrating factor will be, okay, mu of t is going to be e to the power of 6 pi mu a times v divided by m. Oh, my apologies, not b, but t, time t, okay? And that's because, usually differential equations in the form of y prime plus ay, okay, equals to, some constant, I don't know, y of x. Let's just put like, a of x, some constant. When we have differential equations in this form, okay, then, usually the integrating factor is always e to the power of this number multiplied by t, okay? I could prove it to you, I could show you using the, method from scratch, but I think it's just, you get the point, okay? So let's multiply everything by e to the power of 6 pi mu a times t divided by m. So that's our integrating factor. So that means that we're going to have something like this. We're going to have d over dt of our integrating factor, e to the power of 6 pi mu a v divided by m, and then multiply by the velocity. Sorry, this should be t. Okay. All of this is equal to our constant multiplied by the integrating factor. Okay, so the integrating factor again. Great. Now we integrate both sides. Okay, so we're going to end up with something like this. We're going to end up with v of t, okay, is equal to, well, the integral of this is basically 1 over 6 pi mu of a divided by m, okay, so we do the reciprocal of this, multiply by this, and then of course don't forget the constant c, okay, so we're going to have something like this, and we're going to divide this entire equation by e to the power of 6 pi mu a t over m, and then we're going to have something like this. It's going to be m divided by 6 pi mu a, okay, times, well, that's going to be times all this times g minus rho prime 4/3 pi a cubed times g, and then multiplied by 6 pi mu, okay, of at over m plus some constant c, and of course here we're going to subtract the same thing, 6 pi mu at over m, c times e to the power of negative 6 pi mu at over m. This cancels out, okay? So that means that our function, our velocity function, should be something like this, bt equals to, okay, here we can already say that the mass of this object should be, rho, the density, times the volume. So the mass of the object should be rho 4/3 pi a cubed. So I can actually substitute it in here, and we're going to cancel some things out. So let's see what happens. We can factor out a g over here, right? So we're going to have something like this. We're going to have g multiplied by rho, okay, so rho 4/3. But I feel like here we don't need to do that. Let me see something. Okay, so if we do that, we're going to get rho 4/3 pi a cubed, okay, then divided by 6 pi, this pi goes away, mu times a. Okay, so, and then all of this multiplied by, okay, this is going to be multiplied not g, but 1 minus rho prime 4/3 pi a cubed. Okay. And then plus c e to the negative 6 pi mu a t over m. Okay. So over here, what do we got? We got well, we cancel out 2 over here. We get 3. And then we get 9 over on the bottom. Here we get a squared. What else can we cancel out? So let's see. We got, I don't have space, so let me write over here. V of t should be equal to, okay, g rho, and then multiply by 2. Okay, so 2 times this divided by 9. Okay, and then multiply by rho. Okay, and then we have a squared. All of this divided by mu. Okay, that looks good so far. And here we have 1 minus rho prime 4/3 pi a cubed. Okay. All right, guys, so turns out that I missed something, okay? So over here, when I divided by m, okay, you divide everything by m, and it turns out I forgot to divide this by m as well. Okay, so this term is divided by m. So I missed that, I'm sorry. So here, divide that by m, okay? I don't think it changes much. This over here should be, so let's go back. Let's go back to this point. Okay, so let's see. All right, so here, this is divided by m, okay? This cancels out, and we have this term. So when we distribute this, okay, when we distribute the m on, you know, both terms inside of that parenthesis, we're going to cancel out the m over here. So we're going to have b of t is going to be, we can factor out the g, of course. So actually, let's just multiply everything out. So this entire term, bring it in. So you get m, which in this case should be rho 4/3 pi a cubed. So 4/3 pi a cubed. Okay, and then divided by, multiplied by g, divided by 6 pi mu a. Okay, and then minus, and of course multiplied by rho. There's a lot of constants to keep track of, okay? Now, this is going to be minus rho prime, okay? And then, of course, the m's are going to cancel out. So we're going to have rho prime 4/3 pi a cubed g, okay? And then this is going to be divided by 6 pi mu times a, okay? Plus, of course, c to the negative 6 pi mu a times t divided by m. Okay, now, this over here, let's see what, what can we do here. If you see, we can factor out, this entire term. So like this entire term over here can be factored out, okay? And then we're going to get something like this for the velocity. V of t, okay, is equal to, well, this over here is going to be 2 times 2/3, right? And then that's going to be 2 9ths. So it's 2 9ths, okay? And then the pi's cancel. And then mu times, okay? All of this multiplied by g, and then we have rho minus rho prime. So that looks like, okay, the right answer. And then we're going to add the last term, which has the constant of integration, c, multiplied by e to the negative 6 pi mu a times t divided by m. Now, this is the velocity function. Now, how do we find the terminal velocity? Well, you just find the limit of v of t as t goes to infinity. And as you can see, the limit of v of t as t goes to infinity is just going to be this expression over here. Okay, so this goes to zero, as this goes to infinity, it goes to this expression, okay? Because this entire thing will go to 0, right? 1 over infinity is 0, and e to the 0 is 1. And I think they gave us an initial condition. Well, I mean, if you think about it, the initial condition here is that the velocity is 0 at t equals 0, right? So essentially, c is going to be 0, okay? If you, if you find that t is 0 over here, then c should be equal to 0 because the velocity is 0 at time 0, right? You're just dropping it from rest. Okay, so that's the terminal velocity. Now let's see what's the next question. All right, so for part B of this problem, it states that in 1910, Millikan studied the motion of tiny droplets of oil falling in an electric field. A field of strength E exerts a force E times the charge E, lowercase e, on a droplet with charge, E. Assume that the electric field has been adjusted so that the droplet is held stationary, meaning that the velocity is 0, and that the weight and the buoyant force are as given, right, in the beginning. Now find an expression for E, yeah. So Millikan repeated this experiment many times, and from the data that he gathered, he was able to deduce that the charge on an electron was, some magnitude. Okay, so basically, we have pretty much the same setup over here. We have resistive force, we got the buoyant force, and we got the weight. But now we got another force, the electric force. And we want to make sure that, it's going to be floating pretty much. This is going to be at rest. Because the purpose of the electric field is to stop the ball from free falling. So the electric force is actually going to be in the up direction. So it's going to be like that, and it's going to be force E is going to be the electric field times the magnitude of the charge. Okay, so if it's an electron, you know it's going to be the magnitude of the charge of the electron in coulombs. Well, it doesn't matter, it's just algebraic for now. So the question is to find, okay, an expression for E. Yeah, so basically we're going to look for E. Yeah, basically when we find the expression. So it's basically the same thing. We say the sum of the forces, okay, equals to the mass times the derivative with respect to time of, okay, the velocity. And then that's going to be equal. In this case, it doesn't matter which direction you say is positive, because it's just going to be, you know, at rest. So we can say, you know, it's going to be the resistive force plus the buoyant force plus the electric force, right? And then minus the weight. Okay? And of course, because the object, you know, is not moving, it should be equal to 0, right? But we want to use the differential equation to say that it's going to be 0. Okay, so we're going to solve this assuming that we don't know, right, if the object is actually, you know, stopping, if the electric field is contributing. We don't know, right? The problem states that the electric field should be adjusted. So that's why we're going to find E, to find what's the magnitude of E, you know, when, so that the velocity is equal to 0. So we're going to solve for this. Actually, we don't have to change anything in here, not yet. So let's just, you know, bring the one term that's got, you know, the velocity on it. So let's see, we have, so we have dv dt, okay, and then minus, okay, minus the buoyant force. Okay, so the buoyant force, no, the buoyant force doesn't have the B term. So let's bring the resistive force. Yeah, the resistive force, which is going to have, okay, that term. And this is equal to the buoyant force plus electric field minus the weight, okay? And over here, well, it's going to be the same concept, right? The in this case, the integrating factor should be E to the power of 6 pi mu A times B. I'm sorry, times T. Okay? And of course, we're dividing all of this by M, so this should be divided by M. Okay? All right. Now we multiply everything by the integrating factor and we get something like this. We get dv, no, not dv, but d over dt of the velocity multiplied by the integrating factor 6 pi mu A times t divided by m. Okay. All of this is equal to this entire expression, and we're going to integrate both sides. So we integrate this with respect to t. So it's just the integral of a constant multiplied by the integrating factor. Okay, now this over here is going to be nothing but b of t. It's going to be nothing but this entire expression multiplied by m over 6 pi mu a, okay, and then multiplied by b plus e minus the weight divided by the mass cancels, okay, and then plus some constant of integration c multiplied by e to the negative 6 pi mu a t, okay, divided by m. Actually, this should be negative because we got a negative sign over here, so this is negative over here, and so this is going to be positive. Yeah, that's positive, this is negative, and so this is negative. Okay, fine. Now, So when the velocity is equal to 0, okay, we want to find what's the magnitude of the electric charge, right? So, you know, we have the same situation. We have to take, you know, we just set this at t equals 0, okay? Oh, we know that, of course, the initial velocity should be equal to 0, so c is 0. So this term really does not matter. It just goes out, given the initial velocity. And, well, we just set v of t equals to 0, so we have something like this. We got, you know, m, not the m's canceled, so we got 1 over 6 pi times mu times a, all of this multiplied by the weight minus the buoyant force minus the electric field force, and then that's going to be 0. So we're going to find E, which means that, you know, it's nothing but the buoyant force minus the weight, okay? So that's what it should be. Although I'm not sure if let's see what we get. So buoyant force should be Rho Prime times 4/3 pi a cubed times gravity, and then the force is, well, just mg. Yeah, no, I think something's off. Let's see what's going on. Well, here what I forgot to do was I forgot to, you know, express the mass in terms of the density rho. Okay, so we can do that. So we can say that the electric charge is going to be equal to Rho Prime, okay, times 4/3 pi a cubed times acceleration of gravity minus Rho times 4/3 pi a cubed times g. Okay, so the electric charge, okay, should be equal to 4/3 pi a cubed multiplied by g, and then all of that multiplied by Rho Prime minus Rho. Okay, so that should be the final answer. And yeah, so this is a pretty cool problem. Very non-trivial, you know, it's just a bunch of algebra, really. And yeah, that's it. So thanks for watching. I hope you found this useful, and good luck on the exam tomorrow.